हाँ जी, welcome to the 12th lecture, Mathematics for Machine Learning. Last time we were looking at linear transformations, right? Before that we just revised a bit of functions, their definitions, their properties, because once we revise these in the general sense, then it's very easy to just translate that into any kind of functions, right? So linear transformations are the special functions that we are interested in. They maintain the structure, they preserve the structure of vector space, right? So this we saw as very quick revision. We already saw this. The input is a vector space and the output, so the domain and the codomain are vector space. Of course, that is not a given unless we put some conditions on it, right? And these were the two conditions, which is again summing and scaling. Again and again it's a superposition thing. Yeah. So we saw this last time, and then we also defined it, saw this one directly from the function. Exactly वही है, injective, surjective and bijective, right? The key purpose of injective and surjective is to bring them together, to make our functions bijective, to have them invertible. It's a desired property. Not all functions will have it, yeah. But if we can, if we are in a position to design something, we may want to have it like this. Also, if you know that it's not bijective, maybe you know that the solution may not exist. Okay, so you won't be too worried about that, right? Yeah, we also wanted to go beyond that, yes, and say, okay, a homomorphism can be isomorphism, endomorphism, automorphism. All are linear, so they are all homomorphisms. That's a given. But then the isomorphism is just the invertible one. Yes, endo was from the vector space to itself, not necessarily invertible. Yes, and its invertible version is automorphism. So basically you can say that isomorphism is the desired version of homomorphism and automorphism is the desired version of endomorphism. Yeah. So yeah, we saw this. Yes, we also saw this, that it was interesting that two spaces are isomorphic if and only if their dimensions are the same. Yes. So that is why R2 जो है and the complex plane are isomorphic. वो example थी ना, complex plane है एक और एक R2 है जो कार्टेशियन प्लेन है, पर वो दोनों को हम जब लिखते हैं बिल्कुल एक जैसा ही ट्रीट कर सकते हैं. वो इस साइड को हम J कह देते हैं बस. So yeah, iota या J. So that is a very powerful result because it says if and only if. So if you know that two vector spaces have the same dimension, then you know that you can find basically those two vector spaces are isomorphic. You already know that then. Yeah. Okay. और ज़ाहिर है if they are isomorphic, you can always go from one to the other. दोनों तरफ जा सकते हैं ना. It's not homomorphic, not just homomorphic, it's isomorphic. So you can just go in either direction. So you can solve problems as you like in there. Right, so we saw some properties. Yeah, we were here. Yes, what was again and again we often start with equations but then translate them into matrices. We start with functions but then translate them into operation of matrices, right? So linear algebra is mostly about, or a lot of it about application wise is about matrices. Yeah. So there for every linear transformation there exists a matrix. We saw this last time. Yes, that's a claim. And there are some nonlinear ones also that can be represented by matrices, but we are only interested in this. So notice if you have a linear transformation from Rn to Rm, yeah, क्या मतलब इसका जो input है that is a vector of n tuples, yeah, n values हैं, and its output is a vector of m tuple, m values हैं, m बड़ा भी हो सकता है, n से बराबर भी हो सकता है, छोटा भी हो सकता है, ठीक है. So there exists a column vector, x is a column vector, yeah, that's fine. There exists a matrix m by n matrix. This is interesting. Dimension समझ आ रही है matrix की किस तरह मैप कर रही है आपकी इसके साथ, right? The output dimension is here, okay, and the input dimension is the first one. अगर आप matrix multiplication imagine करें तो आपको समझ आ जाएगा, क्योंकि m by n को n by 1 वेक्टर से मल्टीप्लाई करेंगे तो m by 1 आएगा, जो कि is the rm. Yeah, so it's not difficult to check if you forget. Yeah, so ये dimensions उसी के साथ match कर रही हैं, and we will call this the transformation matrix of T. It's the matrix that represents the action of this transformer or this transformation. Yes, so as I said last time, can be found using basis of domain and codomain or range. It's not unique, we saw that last time. Again, remember when we studied basis, I said probably the most important topic in linear algebra, right? ये बार बार आएगा, वो जो इतना बड़ा पीछे theorem आया, just we saw that dimension, if dimension v equals dimension क्या है? The number of bases, right? Again and again, it's all about bases. Eventually we will see that our interest in eigenvalues and eigenvectors is also because of bases. Okay, so all of that comes back to the power of bases. So we saw this last time. Yes, we were here, I think. We just saw some transformation. So we are saying there is a linear transformation that rotates the vectors, and we can find its matrix A. In a later chapter in your book, they actually show you how to find it, but it's not too hard. Actually, today also I'll give you some idea. So this times the each of these vectors, yeah, would give you this thing. So in sub vectors ko agar aap, if you put them all in a matrix, you can multiply A1 times the input matrix. It's like each vector is being operated upon by this matrix, and you're getting a new matrix. जब आप उसको plot करेंगे तो वो rotate हुआ होगा, right? This is used heavily in robotics. If a robotic arm has to grab something and rotate it, then the robotic arm has to know how to control its coordinates, right? Turning वगैरह कैसे करें. And then also in images आप जो flip वगैरह करते हैं, तो उसमें there are mathematical relations written there that in this image every point will be shifted this much, right? And for that you just have a matrix multiplication. Okay, so what's the use of going from Tx, the transformation from the functional notation to matrix notation, right? Basically, as you would guess, it's consistent format suitable for computations, right? Instead of writing in different कभी आप वो cosine sine में लिखेंगे पूरा function, it's the cosine of the x1 plus cosine square of x2 plus sine of x3 plus sine 2 of x4. Instead of that, just take out the cosine sine, put them in a matrix, और वो एक consistent notation बन जाती है. Becomes easier to compare the notation also, and also becomes easier to compute because then you can bring in all the rules of linear algebra, matrix algebra basically, into your calculations, right? So for example, here if you have say a matrix representing this figure, so every value here, these are different values, you can, if you multiply it with the transformation, identity transformation, no change, yeah. You can move it up, move it to the left, rotate it, you can shear it in one direction, shear it in other direction, flip it. Look, flipping का भी वो सारे matrices मौजूद हैं. So we have matrices for each of these transformations, yeah, and it's very easy then. Just everything now is represented by its matrix. कितना shear करना है यहाँ पे वो value रख दें, उतना वो आगे झुक जाएगा. Similarly here it's translated by x y unit. Look, becomes very easy, right? कितना move कराना है उसको, और यही आपके उनके अंदर image processors जो simple हैं उनके अंदर यही चीज़ें encode हुई हैं. Also, second use, transformations can be composed easily. Composition of transformation पढ़ा था हमने, yeah. So you have one function, functions की जैसे composition होती है, basically applying two functions on an input in a series, right. पहले एक function लगाएं, जो output आए फिर दूसरा लगाएं. If that composition is possible and you want to calculate it, and both the transformations are linear, तो दोनों का अपना अपना ट्रांसफॉर्मेशन मैट्रिक्स होगा. तो मैट्रिसेस में इट बिकम्स एज सिंपल एज मैट्रिक्स मल्टीप्लिकेशन. यानी फर्स्ट लीनियर ट्रांसफॉर्मेशन हैज़ इट्स ओन transformation matrix, the second one has its own transformation matrix. If you want to do a composition, assuming that it's allowed, meaning domain and codomain match, yeah. So in that case, this composition matrix is actually, you don't have to find a new one, it's simply this guy, and the input will be either a vector here, some x, or a collection of vectors which will be a matrix, yeah. So that will be your input. So instead of having to solve like this, you will solve simply like this, okay. So ये ज़ाहिर है, it's just computationally consistent and convenient to represent. So now the important question, how do we find the transformation matrix, right. आपके पास कोई transformation का formula है, and now you want to find, okay, how do I translate this formula into a matrix that represents the transformation, right. So let's see, we have a transformation. I'm skipping the word linear now, okay, but ये सारी मैं linear देख रहा हूँ, we're not looking at any other, okay. So consider a linear transformation R2 to R2 with yeah, y and nu defined like this, that's fine. Let's see what this transformation does to the standard basis of R2. यानी ये उसका जो ट्रांसफॉर्मेशन है, ये जो स्टैंडर्ड बेसिस है R2 के, क्या है 0 1 0 0 1, राइट. उसके साथ क्या करती है, उससे हमें हिंट मिलेगा कि इसने बाकी वेक्टर्स के साथ क्या करना है, ठीक, क्योंकि ये वेक्टर्स रिप्रेजेंटेटिव हैं, दे रिप्रेजेंट द होल स्पेस, right. So whatever happens to them has a clue for what will happen to other vectors, yeah. So also, even if you don't know, all the other vectors can be written in terms of these vectors. So then you can still, knowing what happens to these two, you can calculate what will happen to anyone else, yeah. Again, the power of basis. Problem जो है limit हो जाती है. Everything just comes down to basis के साथ क्या हो रहा है. That's it. The whole, whatever is happening there translates to the whole space, yeah. So right. So we normally call them E1 and E2, identity matrix के दो columns हैं, ठीक है. E1 E2. E1 is mapped to phi E1, E2 is mapped to phi E2. I'm writing it very generally now, yeah. मैं ये नहीं लिख रहा कि actual उसने क्या x square कर दिया, उसको cube कर क्या किया, cosine डाल दिया. We can see that later. Now since these are bases, yeah, of course we can write any given vector in R2 like this, right. ऐसे तो हम लिख सकते हैं, ठीक है. अब क्या होगा, this is something interesting. Then V is mapped to, यानी V पे हमने ट्रांसफॉर्मेशन लगा दिया अब phi V, right. तो क्या होगा, V1 phi. Why is this possible, right hand side, वो मैंने उधर लिखा हुआ है. Because precisely because of the definition of linear transformation, right. We said कि if you apply linear transformation, ये क्या थी ना कि phi x है तो then phi, if there is a linear transformation phi x, then phi lambda x should be lambda phi x. एक ये condition थी, वो देखें यहाँ use हो रही है, because you will apply the transformation to the whole thing, yes, but these are scalars, yes. So वो दूसरी क्या थी, this was x plus y was phi x plus phi y, right. Now this thing is phi x in a way, this is phi y, वो lambda पहले ही आपने बाहर निकाल दिए. Both properties help us go in that way, yeah. So because of that I can say okay V is mapped to this thing. समझ आ रही है इसमें कोई मसला तो नहीं. If the bases are mapped to phi e1 and phi e2 then any vector will be a linear combination of the transformed bases. Yeah. So अब इसको मैं इस तरह मैट्रिक्स फॉर्म में लिख सकता हूँ. थोड़ा सा आप ज़रा समझ आ जाएगा ये राइट. ऐसे ब्लॉक में ये ब्लॉक मल्टीप्लिकेशन हो रही है बट यू कैन वेरीफाई दैट दिस इज करेक्ट. राइट. सो वी स्टॉप्ड हियर. ये स्टेप आया था ना. हम कर क्या रहे हैं, ढूंढ क्या रहे हैं, हम ट्रांसफॉर्मेशन मैट्रिक्स ढूंढ रहे हैं. या सो लेट्स गेट देयर. नाउ let's say we want to represent phi ej in codomains standard bases. Okay. Now codomain जो कि R2 है, the function was from R2 to R2. What are the standard bases of the codomain? These are also E1 and E2. Yeah. So what if I want to write this as a linear combination of the standard bases of the codomain, right? अगर codomain R3 होती तो फिर मुझे ये उनकी फॉर्म में लिखना था. ठीक है. लेकिन ये जो कि R2 ही है तो I will R1 होती तो यानी सिर्फ R होती तो सिर्फ एक में लिखना था. But notice now, why are we able to do this? Why should we be able to do this? वो भी same है, right? Also because this vector now lies in R2, right? And we know any vector in R2 can be written in terms of 1 0 and 0 1 लिखा जा सकता है. तो we know it can be written in that form. Yeah. So we write it like that. अभी ये step क्यों किया हमने, अभी आपको नजर आ जाएगा. This is why we did it. अब हम इसके साथ जरा play around करते हैं. ठीक है. And we find ये क्या है. Yes, ये आइडेंटिटी है तो इसका ये तो गायब हो सकती है. राइट. दिस एनी मैट्रिक्स टाइम आइडेंटिटी इज द मैट्रिक्स इटसेल्फ, इट्स गॉन. हियर इज योर ट्रांसफॉर्मेशन मैट्रिक्स. देखिए ये मैट्रिक्स क्या कह रहा है, V is mapped to something times the coordinates of V, and ये new coordinates हैं V के. राइट. V1 we could call them hat, V2 hat are equal to this matrix times the old coordinates. तो ये ट्रांसफॉर्म कर रहा है उसको, ऐसे ही है ना. So we found the transformation matrix. There it is. तो क्या निकला ट्रांसफॉर्मेशन मैट्रिक्स. Basically you take the bases of your domain, right, apply the transformation on them, phi e1 phi e2 उन पे लगा दी, write them in terms of the basis of the codomain जो कि ये था और ये वाला ये था, and then just shuffle around and you will find your transformation matrix. So अभी देखें, all we are saying is that the mapping now can be done like this, right? y1 y2 a phi v1 v2. What were we looking for? A phi. That is the transformation matrix. What is that transformation matrix? These are the coordinates that represent ये a1 1 1 2 ये a2 1 ये है. This one represents the first transformation of the first basis in this form, and this one represents the second basis. Okay, अभी हम कुछ examples भी देख लेंगे, आपको समझ आ जाएगा. So conceptually it seems it's not very hard to find it. Yeah, but we will make it harder. Okay, we will say what if we started with a non-standard basis and wanted to go to another non-standard basis. ये standard to standard थोड़ा आसान है, वो भी इतना मुश्किल नहीं है, कौन सा अभी हो जाएगा वो, लेकिन I wanted to start with the easiest case. Okay, so what if I want to represent domain and codomain in some other basis? Yeah, so abhi we had said okay, here we were saying the vectors and everything is being represented in the standard basis in domain and codomain. Yeah, but okay, let's see if I want to represent it in another set of bases, which could simply be a changed version of the, normally जब हम basis लिखते हैं तो order doesn't matter, yeah, the set वो set होता है, याद है set में order matter नहीं करता, but in transformations the order matters. That's why we always say that the transformations are with respect to ordered bases. अब ये bases वही है ना, सिर्फ order बदला है, आपका transformation matrix बदल जाएगा, ठीक है. So इनको हम अब से क्या कहेंगे, ordered bases. Okay, they are needed for transformation. Now what happens? Okay, let's see. It's not too hard. Because these are still bases of R2, I can write any vector in terms of these or not. And now I'm giving them a different scaling. V1 जो उसके coordinates हैं, इनको हम कहते हैं coordinates with respect to basis 1 and basis 2. Yeah, B1 and B2 basically. So I'm giving them different coordinates now. पिछले वाले मैंने V1 V2 कहे थे, क्यों? Because these values will be different. क्योंकि अब वो bases 0 1 1 0 हो गए हैं. Yeah, basically होता है वो switch कर लिया उन्होंने places, which is fine, but we have tried. अब let's follow the same steps. कुछ भी नया नहीं है. देखिए ना, if this is, then V will map to V1, because this is based on, basically what I did was I applied phi V and I said, okay, what would phi V be? Phi V would be phi of this whole thing, but because it's a linear transformation, I can write it like that. So I wrote it like that, exactly the same. पर अब फर्क क्या आ रहा है थोड़ा सा, you have the transformation matrix over there, yes, but now you also, this one is basically not going away, yeah. So ऐसे ही है ना. So now what you have is, interestingly, this thing. Still, this is your transformation matrix. Okay, here it is, A phi tilde. These are your old coordinates. Okay, and you will have, instead of now y1 y2, which was the the output in the standard basis, it will also be transformed now into your new basis. Yeah. So again, it's not too hard to find this. This is your output. Essentially, it's happening the same way. The output represented in new basis equals A phi tilde multiplied by the input represented in the new basis. Yeah. So the characterization of A phi alone is not enough. You always have to tell us what input basis this guy is taking and what output basis it's taking. So but again, overall, it's the structure is very similar. So let's look at a few important terms that are related to what we just did. Okay, and because अभी तो हमने इसको और आगे लेके जाना है, ठीक है. This was just a very basic thing. First, the definition of coordinates. I already mentioned that, but let's see. Whenever you write a vector in terms of bases, then the values, the weights you assign to each base to get the vector, we call that the coordinates. It makes sense. Cartesian coordinate में क्या coordinate क्या होते हैं किसी point के 2 2 क्या होता है, मतलब आप कह रहे होते हैं कि 1 0 जो basis है उसको मैं 2 दे रहा हूँ, और जो 0 1 basis है उसको भी मैं 2 दे रहा हूँ. Coordinates हों 2 5, तो आप क्या कह रहे होते हैं, मैं जो coordinates 1 0 है उसको 2 दे रहा हूँ और उसको 5 दे रहा हूँ. So we have already assumed ordered bases हमारे ज़हन में होती हैं जब हम coordinates, but in general of course you will have to tell me what your bases are, and based on that I can tell you what my coordinates will be. तो ये जो values हैं, I could write them in a vector, right, like this. Yeah, these are what we call the coordinates of x with respect to ordered basis b1 b2 bn. Okay, so we will actually give them a name. This ordered basis, ये नज़र आ रहा है ordered basis, we give them the name capital B. Okay, and the notation I like, your book isn't using it, but I like this. It's very common in mathematics, and I prefer this one, this notation. We often write alpha as xb. That xb means coordinates of vector x when represented in B, which is B क्या है? Ordered set of bases, not just bases. Yeah, bases का order अगर बदल दें तो B बदल जाता है, ठीक है? Then B बदल जाएगा तो coordinates बदल जाएंगे. आप B इसको Bn कर दें, इसको B1 कर दें तो ये वेक्टर उल्टा हो जाएगा, which is fine. Still it will represent the same vector, but with respect to a different or ordered basis. Yeah. So I'll use this notation from time to time in my slides. When you see this, what am I talking about? I'm talking about this vector x represented in B. So coordinates of x in basis B. Normally हम जब लिखते हैं किसी वेक्टर को x, आप हमें आदत हुई है ना, हम जब वेक्टर x लिखते हैं x is 1 2 3, हम सोच रहे होते हैं ऑर्डर्ड बेसिस जो कि आइडेंटिटी मैट्रिक्स से आती, वो हमने आदत बनाई हुई है, राइट? सो हम क्या करते हैं, स्टैंडर्ड बेसिस का ड्रॉप कर देते हैं, जो कॉमन तरीका है. या इफ़ यू आर यूजिंग द स्टैंडर्ड बेसिस वी जस्ट राइट इट वेक्टर एक्स. हाँ, अगर आप कोई और बेसिस यूज़ कर रहे हैं तो देन यू कैन राइट दी बी सेपरेटली. या ओके, सो दूसरा कोऑर्डिनेट्स हो गया, कोऑर्डिनेट्स वेक्टर हो गया. सिमिलर मैट्रिसेस, the example we just saw, A phi and A phi tilde, they are called similar matrices. That is, they are square and represent the same linear transformation from R2 to R2, although with respect to different bases. ऐसे matrices को हम कहते हैं they are similar. There is another definition coming up जो undergrad में पढ़ाई जाती है, right? But उसके पीछे ये story होती है. तो ये दोनों क्या हैं? They are transformations from the same vector space to the same other vector space, but with respect to different. तो ये दो नहीं है, और जितने मर्जी बना लें आप उन दो के दरमियान, right? So ये similar हैं when they are square. R2 to R2 था ना, but when you have non-square matrices doing the same thing, R2 to R3, R3 to R2, something like that, Rm to Rn, Rn to Rm, then if they do the same thing, we call them equivalent. So similar is kind of a subset of equivalent, right? So when n is equal to m and the matrices are equivalent, then they are also similar. Yeah. So अब ये वो definition है जो हम अक्सर undergrad में करा देते हैं linear algebra 2 में, that if you can write two matrices, नीचे है डेफिनेशन जो स्क्वायर मैट्रिसेस के लिए, देखिए Rn by n है ना, two matrices are similar if they can be, or if there exists a regular matrix. Regular means invertible, yeah, invertible matrix S n by n, that such that they can be written in this form. Later we will see that it's always possible to get this form for similar matrices. Okay. So उसका जो equivalent के लिए क्या है, if they can be written, if they are related like this, if you can find two invertible matrices that can be written, that can give you this relation between A tilde and A, then A tilde and A are equivalent. Okay, and असल में हमारा जो इंटरेस्ट है वो ये वाली बात है, लेकिन this necessarily gives you that, वो आज हम देख लेंगे, ठीक है. So now the general case, how to find the transformation matrix. Let's say we have vector space V and W, दो vector space हैं. Now V is represented by in basis B. अभी हमने किया था standard standard, फिर non-standard to non-standard. अब ये है non-standard to another non-standard. हमारी जो पहली एग्जाम्पल थी उसमें दोनों स्टैंडर्ड थे, दूसरी में दोनों ही नॉन स्टैंडर्ड थे पर सेम थे. अब ये उससे अगला केस है, इसके भी नॉन स्टैंडर्ड हैं, इसके भी नॉन स्टैंडर्ड और दोनों के अलग हैं मना तो नहीं है ना, ठीक है, बेसिस. सो यानी आउटपुट कहता है कि मुझे इस तरह रिप्रेजेंट करो और इनपुट कहता है मैं इस तरह रिप्रेजेंट हो रहा हूँ. फाइन, वी कैन ट्राई टू फाइंड दैट. So the transformation matrix, yeah, so basically what you will do is this. Now look, if you are, ये output कौन सा है इसमें, output के basis कौन से हैं, C है, transfer V to W with yeah, V to W is this, yeah. So you will write, you can write the basis of this. ये सोर्स है, आई लाइक टू कॉल इट द सोर्स और द इनपुट, जहाँ से आप स्टार्ट करें. या यू राइट द बेसिस ऑफ द इनपुट इन टर्म्स ऑफ बेसिस ऑफ द आउटपुट. यही हम कर रहे थे ना पीछे भी, याद है, जो हमने 10 और 01 का फाइल ले लिया था और फिर उनको एक्सपेंड कर दिया था E1 E2 में. सो इट्स एज सिंपल एज दैट, इट जस्ट समराइजेज इट. Take the basis of the input one by one, B1, B2, write them in terms of basis of the output. ये जो coordinate vectors बनते जाएंगे इनको जमा कर लें और वो आपका transformation matrix होगा. बस उसका मैंने आपको glimpse थोड़ा सा दिखा दिया पीछे, right? So this is the general result which gives you. Let's try it here. So if we want to go from V to W and we have ordered bases for V are these and for C are those, and somehow we know these relations, और उन्होंने हमें already वो उनका करके दे दिया. देखिए, the bases of the source input have been written in terms of basis of the destination यानी output. So इधर से क्या था, वो A क्या था, that was just these 1 -1 3 ये वेक्टर में जाती हैं, ठीक है. दैट इज़ जस्ट बिकॉज ऑफ द वे वी, आपने पीछे भी देखा था वो जो मैट्रिक्स बनी तो ऐसे वेक्टर में जाती है, ठीक है. इट्स जस्ट टू कीप द मैट्रिक्स मल्टीप्लिकेशन कन्फर्मेबल. ओके, सो नाउ यू हैव योर ट्रांसफॉर्मेशन मैट्रिक्स. इससे ज़्यादा आसान काम तो नहीं हो सकता ट्रांसफॉर्मेशन मैट्रिक्स निकालना है, ठीक है. आप मुझे बता दें V की बेसिस कौन सी यूज़ करनी है, विच बेसिस डू यू वांट टू यूज़ फॉर V. लेट मी कॉल देम B. या ऑर्डर भी बताना है साथ, ऑर्डर्ड बेसिस. टेल मी विच बेसिस you want me to use for the output. I'll call them C. Yeah. To find the transformation matrix, I will simply write the basis B in terms of, yani linear combinations of basis C. Then whatever coordinates I get, I put them in a matrix form, and that's my transformation matrix. What is this matrix saying? It's saying now if you give me a V, a vector V in V, I can give you a phi V equals Y, which will be in W, but not just that. Yeah, this will be represented in basis B, and my output will actually be in basis C, right? So basis भी cover हो गए, transformations भी cover हो गए, ठीक है. So now हमें चैन तो आता नहीं ठीक है. अब हम कह रहे हैं एक में हमने निकाल लिया था, अचानक हमें ख्याल आया यार बेसिस चेंज करनी है. Should we go back, or is there a shortcut to go between one to? Now they are similar. Yeah, we will show that वो जो हमने T inverse AS निकाला था ना, we'll always be able to find those, and they will be similar or equivalent depending on if they're square or non-square. So how to switch between bases? ट्रांसफॉर्मेशन की बेसिस में स्विच करने से पहले इट्स गुड टू रिवाइज सिंपल चेंज ऑफ बेसिस जो अंडर ग्रेड में पढ़ाया जाता है, ठीक है. जस्ट लाइक रिवाइजिंग फंक्शंस, इट मे सीम लाइक ओके दिस इज़ टू सिंपल स्टफ, पर इट हेल्प्स, आसान हो जाता है दूसरी चीज़ समझ. क्योंकि अगर आप वेक्टर स्पेस के ऊपर इमेजिन कर रहे हैं इंजेक्टिव बाइजेक्टिव, थोड़ा मुश्किल होता है, ठीक है. देन वंस यू अंडरस्टैंड इट ऑन फंक्शंस, देन यू कैन अंडरस्टैंड इट ऑन अ स्लाइटली बिगर कॉन्सेप्ट. या सो before we switch the basis for a phi to a phi tilde, let's see what we know from undergraduate maths, non-standard basis to, let's say we want to change basis of a vector from non-standard basis to standard basis. Let's say I have a vector v written in some basis b of R2, इस तरह लिखा हुआ है, ठीक है. Now I know I can always write it like this also. फ़र्क क्या है? सिर्फ coordinates का फ़र्क है. Coordinate vector हमने पढ़ा ना, coordinates, only the coordinates change. But their sum multiplied by the respective bases should still lead to the exact same vector. Yes, वरना तो मसला हो जाएगा. So if they are same, I can equate them. कर दो, हो गया, right? I can play around with that, right? अब इस equation को पढ़ें. ये तो identity है, standard basis है ना. That's why it's a non-standard to standard. Yeah. So this is your, here we will call this the transition matrix. This is the matrix that is causing the change of bases. Yeah. So if you give me a vector's coordinates in some non-standard basis b1 and b2, I will just multiply that with this b1 and b2, and I can get you v1 and v2. Yeah. So इसका inverse हो जाएगा. If I want to go the other way, if I am given v1 tilde and v2 tilde, and I want to find v1, if I am given v1 v2 and I want to find these, हो जाएगा क्या? ऐसे inverse exist करता है? क्यों? सब स्क्वायर मैट्रिक्स तो इन्वर्टेबल नहीं होते ना. और ये हैं इंडिपेंडेंट, bases are linearly independent, so it will always be invertible. b1 b2 will always be invertible. अगर unless आपने कोई गलत इन्फॉर्मेशन मुझे दी. अगर आपने कहा है कि b1 b2 are some bases of R2, and they should be invertible, और कोई हाल नहीं. बेसिस में आप वेक्टर्स ना ड्रॉप कर सकते हैं ना ऐड कर सकते हैं, राइट? तो ऐसे नहीं, कम ज़्यादा भी नहीं कर सकते. So we will call it the transition matrix. पिछला जो matrix था उसको हमने क्या कहा था? Transformation matrix. वो पूरी transformation show कर रहा था. ये सिर्फ coordinates change कर रहा है from one basis to another. Yeah. Okay. Yeah, you can convince yourself that the inverse exists. So this is what we find then. We find that if I want to go between standard basis and non-standard basis or some other basis, if this is t, this is t inverse. आप ये भी कर सकते हैं कि आप पहले इसको t कह दें और इसको t inverse करें, कोई फर्क नहीं पड़ेगा. वो समझ आ रही है? You can solve them in different ways. So what is the transition matrix based on? Is it's composed of, again, it's composed of the new basis vectors represented in standard form. Okay, so ये आपको समझ आ रही है ये मैं क्यों कह रहा हूँ कि basis B of R2 represented in standard form, यानी B1 B2 को represented in standard basis क्यों कह रहा हूँ? क्यों? यानी लेट्स से आपकी एक बेसिस तो हमें पता है ना, स्टैंडर्ड बेसिस क्या है? 1 0 0 1. Let's say I make another basis 1 minus 1 and 0 1. Okay, let's say. Yeah. So this is non-standard basis. These are b1 and b2. अगर आप इनको प्लॉट करें तो कैसे करेंगे? ये कहाँ आएगा? -1 1 कहाँ आएगा? Yeah. So it will be 1 minus 1. So ये x एक्सिस में 1 है here and नीचे -1 ऐसे आएगा, ऐसे ही है ना. लेकिन आपने ये जो भी प्लॉट किया है, इसको जो आपने प्लॉट किया है, आपने स्टैंडर्ड बेसिस पे प्लॉट किया है इसको, है ना. आपने एज्यूम किया है कि मैंने ये जो लिखा हुआ है 1 minus 1 ये स्टैंडर्ड बेसिस में मैंने लिखा हुआ है, हालांकि हो सकता है नहीं किसी और में लिखा होता. ठीक है. So we always have to be clear that even the bases can be written in different notations. But normally to keep things simple, we are saying that the new bases themselves are written in the standard basis. You कहीं तो रुकना है हमने ना, yeah. So okay, let's try to see graphically what just happened. This is a very beautiful website about linear algebra. You can visit this. बहुत ज़बरदस्त graphics और animations के ज़रिए समझाते हैं ये. So I just took a few, maybe just 2 or 3 images from there to show you. Let's say this is your origin here, yeah, and I tell you that my vector is -1 2, yeah, ये वाला black वाला -1 2. So what I'm saying is that this is the vector because I'm writing it in standard basis, which means I have this standard Cartesian grid in my mind. Yeah, तो वो तो यही बनेगा. अच्छा, अब someone else whose bases are not actually these Cartesian ones, 1 0 0 1 नहीं है, उनकी bases कुछ और हैं, some b1 b2. Yeah, so in a way that is like changing the grid, twisting it, shearing it, turning it. Yeah. Now when this person says -1 2, they don't mean that vector. वो कह रहे होते हैं ये वाला. ठीक है, this is there for them. -1 means what? -1 again towards my first basis. इनकी first basis ये है और second basis, second vector ये है. तो इनका grid तो फिर ये बनता है ना, हमारा ये बनता था. Yeah. Now if their grid is this and they say -1, they mean -1 along this direction. तो वो उसका उलट जाते हैं. ठीक है. When they say 2, they mean 2 along this direction, not 2 along this direction. तो इनका vector और है. Yeah. Now as we saw, what we can do then is to say, okay, the -1 2 seen by this person in the rotated dimension is simply their vector multiplied by their bases. जो उनकी bases हैं, क्या bases बनती हैं इनकी? अगर आप इनकी bases को देखें ना, हमारी terms में ये b1 b2 नज़र आ रहा है, ये इनकी bases हैं. इनको ज़रा कार्टेशियन पे देखें. b1 के कोऑर्डिनेट्स क्या बनते हैं? 2 1, ये देखें. b2 के क्या बनते हैं? -1 1, ये रहे. ठीक है. So their coordinates written in terms of our coordinates, जो कि हम standard वाले हैं. तो in standard, if you multiply the two, you get -4 1. You realize, okay, what they call -1 2, which is this arrow, would be -4 1 for us. अब इसको ज़हन में रखें ये वाले. What we did, we wrote their basis in terms of our basis. ठीक है. अब ये देखें, ये होता their basis in terms of our basis. b1 b2 जो हमने लिखा हुआ है, जो भी होंगे वो, they are being represented in the standard basis. Okay, थोड़ा सा दोबारा देख लेना कहा जाएगा. I know it could be a lot. Basis change वैसे undergrad में करते हैं cover. Yeah, so that is the mapping which we already saw. Mathematically तो निकल आया था ना, लेकिन graphically it helps to have an image in mind. Now we want to make things harder. Yeah, from non-standard to non-standard. Yeah, so okay, let's say I'm saying that B is a basis. I have represented V in these bases, and now I want to represent them in another basis, or I don't know, maybe I want to go from B to C or C to B. We will see, but the formulation would be similar. Yeah, so you agree that the two are the same. They represent the same vector. If we sum them up and multiply by their values, they should represent the same. फर्क कब पड़ता है, वेक्टर डिफरेंट कब लगता है? अगर आप इस ये वाली वैल्यूज़ लें और इन पे प्लॉट करने की कोशिश करें तो फिर गलत हो जाता है. ठीक है. इफ़ यू टेक दीज वैल्यूज़ v1 v2 एंड ट्राई टू प्लॉट देम ऑन दीज बेसिस, ग्रिड बनता है ना बेसिस के लिहाज से. हमें आदत हुई है वो rectangular grid की. Yeah. So then it becomes wrong. But if you take care of the bases and multiply some, then you will always get the same vector. ये तो मतलब वरना तो मसला हो जाएगा. Yeah. So that is how it is. Then now I can rewrite. Notice ये है तो I can rewrite this side as this and this one as here. I can send again y invertible, basis vectors हैं, linearly independent हैं, definitely it will be invertible. So to simplify further, let us represent the basis vector of C with respect to basis B. Okay. So why is it possible? Again, since C1, C2 are vectors in R2 and B is a basis of R2, so we should be able to write C1 and C2 in B1 and B2. Should always be possible. ठीक है. So अब थोड़ी सी game इसमें on है. Again, what I did was I wrote the basis of the source in terms of basis of the destination. ये मैं assume कर रहा हूँ I want to go from C to B. अगर B से C में डालना हो तो आप उलट कर सकते हैं. अच्छा कोई एक निकाल लें तो उसी का इन्वर्स होता है by the way. तो दोनों बारी बारी निकालने की ज़रूरत नहीं होती. Okay. So I just play around with this basic linear algebra किया. We come here. This whole thing now notice cancels out and we are left with this thing. This is transition matrix T from C to B. C to B क्यों कह रहे हैं देखें ये coordinates थे C के है ना ऐसे ही है ना hat वाले and the tilde ones are the coordinates in B. So we are the input is the basis coordinates in C and the output is the coordinates in B. So what is the matrix that we found? That's this guy alpha, gamma, beta, omega. What was that alpha, gamma, beta, omega? What was that? The coordinates of the source because we are going from C to B, coordinates of the source, coordinates of the basis of the source written in terms of the basis of the destination. वो जब लिखते हैं आप उससे जो वैल्यूज निकलती हैं कोऑर्डिनेट्स की वो आपका ट्रांजिशन मैट्रिक्स. So it's not so hard again. Yeah. So you can always get the transition matrix. This is what I said here. Key takeaway is this. So non-standard basis to non-standard basis, yes, just find in one direction, the other will be the inverse. Okay. So not a big deal. And yeah, of course T inverse will always exist because आगे हम rules पढ़ेंगे matrix inversion के A B whole inverse is equal to B inverse A inverse given that the inverses exist. अगर ना exist करें तो equality hold नहीं करेगी. But since we know these are basis matrices, basis their inverses will always exist, so not a big deal. Yeah. Okay. So let's look at an very quick example here. Let's say B has there are bases UW and another basis U prime W prime, and let's say you are told that U prime can be written as AU plus BW and W prime can be written as CU plus. So find the transition matrix from B prime to B. क्या होगा? वो हमने उधर तो वो होगा AC BD ऐसे ही. Yeah. So basically you write the basis of the source, which is in this case B prime, in terms of basis of the destination. उससे जो coordinate matrix निकलेगा that will be your, and its inverse will be the other way around. Yeah. क्या जी जो इसकी बात करें हाँ ये वाला, this matrix will take your vectors from basis b prime to b. okay, यहाँ आपको लग रहा है कि it's going from b to b prime, यही करना होता है. ट्रांजिशन मैट्रिक्स में उल्टी चीज़ निकलती है, ठीक है. वो जो हमने पीछे शो किया था ना, इवेंचुअली इट बिकम्स, अगर आप इसको दोबारा देखें ना, ये पूरा कर आके यही निकलता है कि इट्स ऑलवेज इन रिवर्स. ओके, सोर्स के जो सोर्स bases are written in terms of destination basis, and then this is multiplied with the source. या तो वही निकलता हो. आप उसको जो देख रहे हैं वो इधर से नहीं देखना है, ये ट्रांजिशन नहीं कर रहा, इससे हमने ट्रांजिशन मैट्रिक्स निकालना है. देन द ट्रांजिशन मैट्रिक्स विल डू दिस. एंड अच्छा, बी प्राइम, बी टू बी प्राइम क्या होगा फिर, उसका इनवर्स, right? So you can find that, and you know it will exist, okay, because those are bases. Okay, let's try this. Let b and b prime, again I am saying they themselves are written in standard form. अगर ये खुद भी स्टैंडर्ड में ना हो तो फिर आप वो जो हमने किया वो नहीं चलेगा, पहले इनको स्टैंडर्ड में लाना पड़ेगा आप. ओके, तो करें जी जल्दी से पेपर पे. So we want to find the change of basis matrix from B prime to B. Shortcut याद हुआ अभी तक या नहीं? Basis of the source written in terms of basis of the destination. बड़ा इसका सादा जवाब है, कुछ करने की जरूरत नहीं है. बिकॉज यू ऑलरेडी हैव सो बेसिस ऑफ द सोर्स विच इज़ बी प्राइम रिटन इन टर्म्स ऑफ बेसिस ऑफ द डेस्टिनेशन, क्योंकि डेस्टिनेशन मैंने आपको आसान वाली दी है, स्टैंडर्ड दी है, तो इट्स ऑलरेडी रिटन इन दैट फॉर्म. सो द ट्रांजिशन मैट्रिक्स इज सिंपली 3 1 minus 2 1. Yeah, so notice the bases of the source have already been written in terms of basis of the destination, which is standard. So I already said they were in standard notation. So your transition matrix is this guy, and you can test that it will convert. And the so the other way around, you can even verify now. Yeah, वापस जाना हो तो p inverse use होगा, right? So if you had a vector v represented in b prime, it was 2 1. In b it will be represented 4 3. If you want to check you're right, apply the inverse, which will be p inverse, and you should get 2 1 back. Yeah, so okay, अब थोड़ा सा ट्रिकी हो गया. पिछला आसान क्यों था सवाल? पिछला इसलिए आसान था कि जो आपने जो करना है वो पहले ही लिखा हुआ हो. The bases of the source have to be written in terms of basis of the destination. If the destination happens to be standard destination, then you've already written them in standard form. So वही होते हैं. Now ये थोड़ा different है क्योंकि now the source and destination, both of them, they are in खुद वो standard notation में, but the destination is not standard. Yeah. So अब हाँ, दोनों खुद स्टैंडर्ड नहीं है, लेकिन अगर आप इनको प्लॉट करेंगे तो ये है, ये उसी पे कार्टेशियन जो रेक्टेंगुलर पे दिखा रही है, राइट. अच्छा, निकालें जी बी टू सी जल्दी से. आइडिया है करना क्या है, यू नो द ट्रिक नाउ. So you want to write basis of the source, which is b, in terms of basis of the destination, it is C. So this is what you should get. थोड़ा सा आपको you'll have to play around and you can find this thing. Because this is a very small toy example, you can play around and find this thing, yeah. But when we solve for real systems, bigger let's say problems with bigger dimensions, we have ways to find this projection, okay. वो फिर हम बाद में देखेंगे exactly, लेकिन principle वही है. Okay, so why did we go there? Actually this was our question. वो तो अभी हमने ऐसे ही छोटा सा किया है ना, right? What was that? You have a vector written in basis B and you want to write it in basis C, right? ये अभी तक हमने वो basic सा किया. What we are saying now is you found a transformation matrix A phi which went from say basis B to C, yeah. This guy, let's say this guy was a transformation from V to W, okay, and V was represented in some B and W was represented in some C. Now you want to find the transition matrix. What would the transition matrix would have been if V had instead been written in some other basis and W also had been written in some other basis? पूरा general कर दिया, ठीक है. Of course specific cases इसके होंगे कि you might have B and B here but only C changes. You may have C and C here and only B change, but this is the most general form. Input was in B, output was in C. Now I want input in B tilde and output in C tilde. That transition matrix we will say call A phi tilde. So like the transition matrix, I will do this in two steps. The first one will be where I will only change one of them, and that will be for this case. This is the easy case, relatively easy case, which is what the input was in basis B, the output was in basis Y. Now and I had found some transition transformation matrix जैसे हमने पहले निकाला था, and now I want to find the other transformation matrix which correspond to this guy, but it works on B tilde and B tilde. Now for the input space and output space to have the same set of bases, their dimension has to be same. So this is actually talking about square transformations, okay. वो जो हम अगला करेंगे वो general होगा, फिर rectangular हो जाएगा, yeah. That will cover this, but it's easier to follow at this stage, so let's do that. ये तो given है, ठीक है. We are saying that A phi is a transformation matrix that carries out the transformation of a given vector in basis B and displays its output also in basis B. ये तो मैंने आपको given है, अब find आपने वो करना. Let T be a transition matrix from B to B tilde. अभी हमने निकाले हैं ना general, उस तरह आप निकाल लेंगे, ठीक है. वो आ गया, मैं दोबारा नहीं दिखा रहा वो कैसे निकाल, ठीक है. T आ गया. अच्छा, if T is a transition matrix from B to B tilde, you would agree that applying T to YB will make it, agreed, ठीक है. Apply it to the right hand side also, okay. If you apply it to the right hand side also, yeah, it keeps going, but on the left now. But YB tilde is what we want, right? A phi tilde VB tilde, yes. But this is again now एक और trick हम एक और step करेंगे, which is what we know that VB tilde is T VB. दो दफ़ा लगाया मैंने T, ये सिर्फ juggling है just to get the shape we want, ठीक है. ये नहीं है कि ये कोई मैजिकली किसी को पता था कैसे ही करना है, मतलब ट्राई कर करके फिर वो एक दो हो जाता है तो दैट सिंप्लीफाइज. So just don't worry about this. All I did was I said let's say there is a transition matrix B to B prime B tilde, वो हमने find किए हैं अभी general T. Yeah. So if that is the case, then I can apply T to both sides. If I apply it to both sides, I get T by B. Here I get T, multiply that. But T by B is y B tilde. I translate, यही तो करना उसमें. B to B tilde जाना था, so it went from B to B tilde. But I know that y B tilde is the output of that guy, supposedly. Yeah. Then if that is the case, I can write like this. But then because T goes from B to B tilde, I can write VB tilde as TVB. Now this is here. ये क्यों किया मैंने अभी, वो आपको अगला स्टेप नजर आ जाएगा. Now I can say that A phi, ये नजर आ रहा है आपको क्यों किया, अब इनको मैं सेम लाना चाह रहा था, नजर आ रहा है या ये कवर का. Why did I make this step? Because here, because I wanted this to be same on both sides. Why does that help? Because then I can say these two have to be equal, है ना, वही जो आप बेसिक अलजेब्रा में जो सिंप्लीफिकेशंस करते हैं. If these have to be equal, then I have the result I wanted. याद है सिमिलैरिटी की जो डेफिनेशन हम वो यहाँ से निकलती है. We say A phi tilde and A phi are similar if there exists an invertible matrix T such that they can be related like that. Okay. और linear transformation के point of view से similar matrix means that these matrices carry out the exact same transformation, although it's represented in different bases. That's all. Right. तो effect same होता है पर bases की representation में फ़र्क होता है. And T inverse, this only works for square matrices. Okay, similar होते हैं square के लिए. अब हम equivalent वाला देखेंगे जो हमने किया था, but it will be exactly the same. नहीं, diagonalizability में तो requirement है कि the matrix in the middle should be diagonal. We say a matrix is diagonalizable if there exists a diagonal matrix such that A equals sigma D sigma inverse, where D is the diagonal. ये उससे थोड़ा कम है, वो फिर एक और restriction है, right? कि then A phi will have to be a diagonal matrix. अभी हम वो नहीं कर रहे, but yeah, उसका निकलता ऐसे ही है कुछ. वो होती है, वो सिमेट्रिक के लिए होती है. फिर वो आप हाँ आप लोग भी उसके ऊपर और कंडीशंस लगाते हैं, वो आएंगी आगे. मैट्रिक्स डिकम्पोजिशन चैप्टर है पूरा. बट यू आर राइट, वो उन पे लग, अभी हमें नहीं उसकी जरूरत. हमें अभी पता है कि टी इन्वर्टेबल है. क्यों? इट्स अ ट्रांजिशन मैट्रिक्स. वो ट्रांजिशन मैट्रिक्स क्या था याद है, वो हमने जो निकाला था उससे बेसिस की रिप्रेजेंटेशन से. या so this is how it is. Now let's do the general case. ये मैं आपको बता रहा था general case. We say that I know there is a transformation matrix that works on VB and gives YC, Rn to Rm, general. अब I want to find its equivalent matrix that has the same effect but represents input in B tilde and output in C tilde. तो कोई इतना बड़ा मसला नहीं है. अब हमें दो मैट्रिक्स चाहिए होंगे बस. ठीक है. Let S be a transition matrix from B to B tilde. Let T be a, पिछली दफ़ा एक ही चाहिए था क्योंकि दोनों ही इनपुट और आउटपुट दोनों ही B से B tilde पे गए थे. अब दो ट्रांजिशंस हो रही हैं. B is going to B tilde, C is going to C tilde, दोनों चेंज हो रहे हैं. ऐसे ही है. So in that case we need two transition matrices, not a big deal. We can, आपने पहले देख लिया कैसे फाइंड करते हैं, उसी तरह ये निकलेंगे. So same story, same tricks, but this time ये जब हम स्टेप करेंगे, let's see. So I multiply both sides by t, find t by c, t here. This becomes t is c to c tilde. So yes, c to c tilde, but this should be a tilde v b tilde, which is t a phi v b, and left hand side. Now the right hand side, ये वाला, ये क्या हुआ स्टेप, ये समझ आ रहा है? इसको मैंने क्या किया, I replaced it with S inverse V B tilde. Why? Because S is from B to B tilde. I am going from उल्टा नहीं है, transition matrix for B to B tilde. So अच्छा S inverse लगा रहे हैं ना, right? So S is from B to B tilde, but I am going from B tilde to B. So I will use S inverse, right? उल्टा उसका लगेगा. So if they are now again पहले की तरह these are same, so फिर इसका मतलब है कि these should be same, right? That is your equivalence relation. Okay, so now you are able to find a phi. So we have answered the question how to go from a phi to a phi tilde, और उलट भी जा सकते हैं because t and s are both invertible. So just दोनों तरफ से multiply करें एक एक, तो आपको you can get, if you know a phi tilde, you can find a phi. Yeah. Now in summary, this is what I am writing just to keep it clear. If you want to go from a phi to a phi tilde, then multiply it with t c to c tilde and s inverse b to b tilde. Sometimes, like in your textbook, they like to write it in c tilde to c, which should be inverse of this, right? So okay, you could just have it there. कोई मसला नहीं है, बस वेक्टर का नाम sort of नाम बदल जाएगा और कुछ नहीं होगा, right? So and this is the definition of equivalence also, right? So अब आप समझ आ रही है कि why हम क्यों कहते हैं जब basically in algebra में कि ये equivalent हैं या similar हैं, because their effect is similar, the effect is equivalent because they both represent the same transformation, right? Although in different bases. So let's take a quick look at an example. You have phi R3 to R4. Phi x you have its transformation matrix A, but this transformation matrix is based on these. Notice they are standard. Fine. Now we want to find a phi tilde, which is takes the vector in some non-standard basis B tilde and gives the output in another non-standard basis C tilde. So all you have to do is find the transition matrix कहाँ से कहाँ का, from here to here or here to here, yes, and इधर से इधर, yeah. So we have done that, हमने पीछे किया है वो, right? How to find that? So you can use that. For example, here we already know SB tilde to B. Where is that? Yeah, SB tilde to B, the transition matrix from B tilde to B. What was that जो हमने shortcut लगाया था transition matrix का? You write the basis of the source in terms of basis of the destination. अब ये तो source B tilde to B है, तो source के तो already इसकी term में लिखे हुए हैं, right? This is the standard form में इनको हम लिखते हैं. So basically you already have the answer. You have SB tilde to B, you have TC tilde to C, so just plug those in here and you get this. Yeah. ये थोड़ी सी आपकी practice लेगा, थोड़ी सी आपको revision, there's a lot going on, but once you understand it, it's very simple. Okay, कोई उसमें कुछ बहुत ज़्यादा वो नहीं है, analytical depth नहीं है इतनी. Right, having अभी तक हमने क्या किया? Basically we said every linear transformation has a matrix associated with it. We found that matrix, yeah. But then we said, well, we were just talking about standard input, standard out, meaning standard basis. So what if we want to juggle that? वो हमने सारा अभी तक किया, बस और कुछ नहीं है, आज आगे वही था. Now we want to characterize the properties of the linear transform. Functions की हमने कैसे की थी, उनकी रेंज क्या है, उनका प्री इमेज क्या है, राइट, उनके लेट्स से नल क्या है, कौन कौन सी वैल्यूज़ हैं इनपुट की विच आर मैप टू द नल 0, right, those kind of things. So same thing we want to do here, and when we do that it leads to very important concept, the 4 fundamental spaces, subspaces. The 4 fundamental spaces, subspaces are those vector spaces that are associated with a linear transformation and its corresponding transformation matrix. जब आप ट्रांसफॉर्मेशन में उनका नाम लेते हैं तो आप उन्हें कर्नल कह देंगे, कर्नल ऑफ द ट्रांसफॉर्मेशन. जब आप उसकी बात करेंगे इन टर्म्स ऑफ ए द मैट्रिक्स, यू विल से नल स्पेस. ठीक है, हैं दोनों एक ही चीज़ क्योंकि फाई एंड ए आर इक्विवेलेंट, या डिफरेंट वेज ऑफ सेइंग इट. सो इसी तरह द नेम्स विल बी डिफरेंट पर उनकी डेफिनेशन एक ही होगी, या उनका इफेक्ट एक ही होगा. सो लेट्स लुक एट दोज. These are the 4 fundamental spaces. You should be very intimately familiar with them. Okay, they are kernel, image, co-image, co-kernel. Okay, so that's when I talk about the transformation. If I talk about its corresponding matrix, I will talk about null space, column space, row space, and left null space. Yeah, A is not necessarily square, fine. So this is a, इस इमेज से कोई समझ आ रही है. डोमेन को डोमेन तो we know from the functions we saw, right? Domain को डोमेन, what are they? Sorry, क्या? आइडेंटिटी आप एडिशन के लिहाज से कह रहे हैं, यानी ज़ीरो की बात, नल वेक्टर की बात करें, राइट, या. सो व्हाट एल्स डू यू सी हियर, व्हाट इज इमेज? इमेज उसमें भी ऐसे ही था, फंक्शंस में भी, राइट. सो इमेज इज द बेसिकली जिसको हम वहाँ क्या कह रहे थे फंक्शन में, रेंज कह रहे थे, या. सो इमेज ऑफ अ गिवन पॉइंट इज व्हाट इट शोज हियर. इमेज ऑफ द होल domain is the basically the image that we call image, right. So let's look at it. Kernel, set of all vectors in V, set of all inputs which will be mapped to a null, okay, to the 0 vector in W, yeah. इसी का equivalent null space है which is the same. It is set of all V such that A V equals 0 W. दोनों एक ही बात कह रहे हैं, ठीक है. So nothing special there. So in a way null space ये बाद में बड़ा काम आएगा हमारे. ये जो आप निकालते हैं ना जनरल सोल्यूशन और पर्टिकुलर सोल्यूशन, ये वो काम है, या. So in a way null space is the solution space for the homogeneous equation AV equals 0, yeah. Image basically again yes, as you have already guessed, it's the range, जिसको हम रेंज कहते हैं. इसका वेक्टर्स में मैट्रिक्स के लिए क्या नाम है, ऊपर लिखा है मैंने, कॉलम स्पेस. ओके, बिकॉज व्हाई डू वी कॉल इट कॉलम स्पेस? नोट ए वी विल लीड टू डब्ल्यू, बट यू कैन ऑलवेज, अगर आप ए को कॉलम्स की तरह देखें ना, तो यू कैन सी दैट यू आर एक्चुअली मेकिंग लीनियर बाय पिकिंग डिफरेंट वैल्यूज ऑफ वीज, वी के जो कोऑर्डिनेट्स हैं, by picking different values you are actually making linear combinations of the columns of A करके देख सकते हैं आप. तो फिर ये A की column space generated by linear combinations of A, ऐसा ही है ना. तो definitely image is actually the column space of the matrix A, right. Left null space and row space, they are related to a kind of a corresponding transformation which will be enacted by AT. Okay, ये कुछ और हो सकती है, लेकिन बहरहाल वो A की transformation थी represented by A. Now the transformation represented by AT will have a left null space or co-kernel, which will be, अब ये interesting, set of all W in W for which ATW is mapped back to 0. अब इसमें ये this is a subset of W. null space किसका subset था? V का. ये important है, या? Null space, the kernel was a subset of V, whereas co-kernel or the left null space is a, और इसको मैं इस फॉर्म में इसलिए लिखा है just to show you why we call it left. ये वहाँ पे A था ना, ऐसे था ना, xt नहीं सॉरी A x था, है ना, 0W, that was null space. A V था, sorry, that was null space. But if you want to write the left null space, it's take a vector from W T A times, तो ये left से multiply हो रहा है इसलिए बस इसको left कहते हैं उसके बाद, ठीक है, left null space. And in terms of psi it will be called co-kernel. Row space, now it is the linear combination of the rows of AT, rows of A, meaning the columns of AT. Now I am not going to prove it here, you can check, but row space of A equals column space of A T. Okay, yeah, this is straightforward, sorry, ये तो मतलब वो एक ही बात कह रहा हूँ. Right, so let's see now the general case. Actually this is a special case, I should call it, because now I want to lock V to Rn and W to Rm. Maybe I should call it more common case, because general was this one, क्योंकि हमने कहा कोई भी VW, right, अब हम उनको fix करने लगे हैं, but usually it's these guys that we work with, so it's more of a mistake here, it should be called common case. So column space of a matrix, when we say column space of a matrix, we are always assuming that the matrix is going from Rn to Rm, yani V is Rn and W is Rm, or n and n could be equal to m, that's fine, but it's general. So it's the basically the space spanned by the columns of A. Span पढ़ा था ना हमने किसी vector set. So basically it's the all the possible linear combination of the columns of A. Yeah, okay. For example, if you have matrix A like this, these are its columns, right? सही है, इनको अगर करें तो इसकी क्या बन रही है, स्पेस ये प्लेन बनता है, राइट, एक एक्स्ट्रा है इसमें, राइट, इट्स नॉट कॉल, दिस इज नॉट अ बेसिस, वो नहीं है, ज़रूरी नहीं है, या. सो द कॉलम स्पेस ऑफ ए इज दिस प्लेन, क्योंकि उसके तीनों वेक्टर्स, उसके जो तीनों कॉलम है वो इसी में है. सो अब इनका कोई भी लीनियर कॉम्बिनेशन बनाएंगे वो इट विल स्टे इन दिस प्लेन. या रो स्पेस ऑफ अ मैट्रिक्स, उसी मैट्रिक्स की रो स्पेस क्या है, सी दी linear combinations of the rows of that same matrix. Yeah, अब देखें, if that was a plane, this 2D plane, this is still a plane, पर अभी ये 3D में कहीं पड़ा, हाइपर प्लेन है ये, राइट. यू कैन सी 1 to 1 will now, क्योंकि अब 3 कोऑर्डिनेट आ गए ना, तो it's now in R3, but it's still a plane. Inside R3 it's still a plane. Yeah, in fact we will see that the rank of column rank has to be the same as the row rank. वो जब आएगा तो फिर हम देख लेंगे. Yeah, okay. Null space of the matrix, again we already defined that. It's the null there. So image and kernel of a linear mapping, let's look at that. ये सिर्फ आपको आइडिया देने के लिए as an example here. Yeah, so it's rather straightforward. We will use some tricks sometimes to get here in calculations, but अगर आपको आइडिया है तो it's very straightforward. Kernel phi is the span of the bases here. ये image phi is the span, these are the columns. Yeah, So basically इनका span यानी all of their linear combinations. Why are they saying kernel is the span of this? What they did was they found the solution space of Ax equals 0, and they found their basis vectors, or they said okay, un basis vectors ka span will be the null space, right? Because if these two are mapped to 0, all their linear combinations आप check कर सकते हैं will also be mapped to 0. So there will be a span of these two, right? तो वो आप example बाद में देख लेना. Why are we interested? Again सारी कहानी हमारी जो है ना solution sets, analytical solutions, इन पे आ जाके ख़त्म होती हैं. So it's got to do with equations, solving equations, looking at solution sets. So like example this one theorem, a system Ax equal to B has a solution, meaning at least one solution, if and only if B is in the column space of A. Agree करते हैं आप? है? समझ आ रही? क्यों है ये? You can already tell if the solution will exist or not if you know the column space of A. If B is not in the column space of A, there is no solution to this. क्यों? देखिए ना, इस equation को पढ़ें आप. ये क्या कह रही? What is this equation saying? This is saying that B is a linear combination of the columns of A. यही कह रही है ना? वो तो column space होती है. So then B has to be in its column space. अगर नहीं है तो ये equation inconsistent hai, you won't find a solution. Yes, so yes, that is the reason. Now later we will define orthogonality exactly, but just to give you an idea, it also helps us. जो मैं वजह बता रहा हूँ कि why are we interested in column space, null space, and those things. Actually, we have results on them which are very helpful. Like row space and null space are orthogonal complements of each other. What does that mean? एग्जैक्टली इसका ये मतलब नहीं है कि वो ऐसे पड़ी हुई है कहीं पे. इसका ये मतलब है बेसिकली, ये वैसे ही दिखाने के लिए होता है. इसका ये मतलब है एवरी वेक्टर इन नल स्पेस इज ऑर्थोगोनल, जो कि हम 90 डिग्री कहते हैं, लेकिन एक्चुअली इट कैन बी, देयर आर अदर डेफिनेशंस, वो हम इनर प्रोडक्ट जब पढ़ेंगे नेक्स्ट लेक्चर में इंशाल्लाह फिर देख लेंगे. बट एवरी वेक्टर इन नल स्पेस इज ऑर्थोगोनल टू एवरी अदर वेक्टर, एवरी वेक्टर इन रो स्पेस. ठीक है? That means a vector cannot lie in both the solution to the to null space and the row space, and together they form the whole space. Yeah, इधर ये complement का part जो है, that is this one, and here we have the other one. Yeah, okay. So we will see exact definition of that later. So this is what it's showing. Let's say I know that the row space is this hyperplane. तो फिर आप automatically मुझे बता सकते हैं कि null space क्या होगी? क्या होगी? नजर आ रही है वहाँ पे? Right? So the null space will be this line. Why? Because null space, if I know the row space, then the null space can only be that space कि उसमें हर vector will be orthogonal to every vector in the row space. और आप बस एक ही option बचती है वो ये line है. So you can already talk about the range of the solutions, where will the solutions lie, and all those things, right? आप लोगों की अगली क्लास है? अच्छा, presentation है, right? So I'll just finish this linear algebra part today. So bear with me. Rank and nullity. Rank का पता है आपको? Matrix rank होता है, right? So let's link them to fundamental. First remember, आपको याद है हमने जब वो game of unknowns किया था, right? So we saw that if you had this kind of equations, yeah, they were overdetermined, only two independent equations. So I said their true worth or rank was actually 2. Yeah, so that is the concept of rank basically. We will define it now formally. The column rank of A is the maximum sized subset of columns of A that are linearly independent. Yeah, so you know the row rank similarly. Now this is interesting, you will have to find it on your own. The row rank is always equal to column rank. Okay. So examples of rank here. First one, its rank is 2. The second one is also rank is 2. Usually in undergrads we teach Gaussian elimination, pivots बना के वो करते हैं और फिर वो जो निकाल लेते हैं. Basically you can use that. Yeah. Now the link with rank. What is the link of these with rank? The dimensions of the image of phi. Now image of phi is the same as the column space of A, which is the same as the row space of A. इनकी dimension is always equal to the rank. Dimension का मतलब क्या? Number of bases that will represent this space. Yeah. Nullity, that's another thing we define. It's the dimension of the null space, kernel or null space of A. Now there is a very powerful theorem called the fundamental theorem of linear mappings. क्या है? सुना है? Rank nullity theorem. Yeah. It says that rank plus nullity is always equal to dimensions of the V, the source. Okay. So that usually helps us find a lot of other results on that. So notice that the rank and nullity, because they are orthogonal complements, you can verify that the rank plus nullity will in this case will always be 3D. अभी देखें row space अगर ये plane है तो we already said the only option for null space is this guy. What if the row space is a line? Then the only option for the null space is to be a hyperplane orthogonal to that. Yeah. So in both cases देखें बनता क्या तीनों के vectors मिलाएं. This plane plus this vector is R3. This plane plus this vector is again R3. So that is the rank nullity theorem in practice. So you can read these on your own. I'll just flash them here. Chand results हैं on the rank nullity thing. If null A is just the 0 vector, A is invertible, and Ax equal to B has a unique solution for any vector B. Similarly, ये हम already discuss कर चुके हैं. If rank of A is equal to rank of A augmented with B, only then there is a unique solution. क्यों है ये? If rank A equals rank A को लिखें और उसके साथ B भी लिख दें, दोनों का रैंक बराबर हो तो क्या मतलब होगा इसका? हाँ, लेकिन इस दोनों के रैंक बराबर है क्या मतलब? वो तो कॉन्सिक्वेंस हो गया ना. मतलब बी ने कुछ नया ऐड ही नहीं किया उसमें. ऐसे ही है ना, अगर दोनों का रैंक बराबर है तो बी ने कुछ भी नया ऐड नहीं किया. किस सूरत में वो नया ऐड नहीं करता? जब वो लीनियर कॉम्बिनेशन हो पहले ही उसका. ठीक है, तो इट्स द सेम थिंग बीइंग सेड इन अ न्यू वे. We are saying that the new column you added did not add to the rank because it was already a linear combination of A. तो इसने कोई नया rank उसके अंदर add नहीं किया. So similarly you can see the column space पे कुछ results हैं. I'll just let you read those on your own. Yeah, a lot going on there. ये समरी है इनकी, ये भी आप खुद ही देख लेना. I already told you that orthogonality, rank nullity theorem, ये रहा rank nullity theorem, okay, which is useful. A quick revision of the affine subspace याद है? At some point we wanted to say, okay, what if I take a subspace U and translate it, shift it by a vector. ये हमने किया था, आपको याद होगा, right? That may not qualify for a subspace, especially if this xt is not inside the original one. इसके अंदर ही हो तो फिर ये still subspace होगा. If it's outside this plane where this subspace is, then this new space, although we call it a subspace, we call it affine subspace, but it is actually not a subspace. And why इस केस में क्या वजह है? Simply इसमें पहली बात origin ही नहीं है इसके अंदर ना, zero नहीं है, null exist नहीं करता इसके अंदर, right? So affine subspaces are useful because they give us the solution to the general equation, this one, ax equals b. Why is that? For example, ax equal to 0 forms a subspace that we call the null space, right? E.g. x0 is a solution, then x equal to v, x are solutions, इनके linear combinations भी solution होंगे, yeah. But for this one, if b is not 0, this does not form a subspace, showing that the solution Ax will forms a affine subspace. Very simple. Let's say we have u in the null space of A, ठीक है, उसके अंदर है. Then u is a solution to homogeneous equation. यही आप करते हैं ना, पहले आप एक जनरल सोल्यूशन निकालते हैं, ये आप ये कर रहे होते हैं, राइट? फिर आप एक निकालते हैं पर्टिकुलर सोल्यूशन. If there is a solution x naught of b, then I can show that x naught plus u, where any u from the null space can be added, this space is now a affine subspace, is a solution to this. समझ आ रही कैसे होगा? लिख के देख लें. ax naught plus u equals ax naught plus au, but au is in the null space. ठीक है, तो फिर au has to be 0. You have ax naught equals basically ax equals b, yeah. So that is the solution. Solution set of ax equal to b is either empty, or it is the affine subspace formed by translating null space by a particular solution. ये आपको पूरी रेसिपी मिल गई है सोल्यूशन निकल. क्या करें? होमोजेनस इक्वेशन सॉल्व करें, उसका जो सोल्यूशन सेट है दैट इज द नल स्पेस. देन सॉल्व, गेट वन सोल्यूशन फॉर द पर्टिकुलर इक्वेशन, यूज दैट एज द ट्रांसलेटिंग वेक्टर. पूरी की पूरी नल स्पेस आपका सोल्यूशन है, जस्ट शिफ्ट इट बाय that support vector, yeah. So we call it the translating vector, support vector, कई नाम है इसके, affine subspace. So we already defined that one. Yeah, this we also defined. You can also have affine mapping, where what you have is, पहले ये थी ना, ये क्या थी? Linear mapping, linear transformation. Take the linear transformation and shift it by a vector in the destination. ये कभी कभार आगे हमारे काम आएगी डायमेंशनैलिटी रिडक्शन में. ये लास्ट टॉपिक है इसका, हमारे चैप्टर का एंड टॉपिक का, मॉड्यूल का, लीनियर अलजेब्रा में. दिस इज जस्ट आउट ऑफ इंटरेस्ट, दिस इज नॉट एक्चुअली इन देयर. दे ओनली स्टॉप एट अफाइंड सबस्पेस. अफाइंड स्पेस क्या होती है? क्या सुना हुआ है? सो basically we say it's a space that has forgotten its origin. So what happens if we drop the origin of a Cartesian plane? हमें आदत है ना origin से शुरू करते हैं आज. अगर हम origin drop कर दें फिर क्या होगा? यानी origin गया, अब ये point जो red point है, because of the origin it was a vector, the point could be represented in coordinates. If you take away the origin, the point is just a point, right? So points are no longer vectors. Adding and scaling of points makes no sense. You cannot, vectors की जो addition वगैरह वो हर कोई अपने origin के लिहाज से करेगा तो अलग अलग निकलेगी, ठीक? And you can still measure the distances, but there are many other things that change. This is the conventional geometry, okay? जो पहले यूज होती थी दुनिया में विदाउट द ओरिजिन. किसने इंट्रोड्यूस कराया था ओरिजिन? कौन था? मैथमेटिशियन फ्रांस का. उसके नाम पे आप इसको कोऑर्डिनेट सिस्टम में, डेकार्ट, उसके नाम का जो सेकंड पार्ट है ना, कार्टेशियन, या डेकार्ट. सो it's the origin that makes a point a vector, otherwise a point is just a point. This guy is the one who introduced and he, because of that idea, and then he was able to identify coordinates, he laid the foundation of entirely new geometry called एनालिटिकल ज्योमेट्री. इससे पहले जो ज्योमेट्री थी वो अब हम उसको कन्वेंशनल ज्योमेट्री कहते हैं. दैट हैड नो ओरिजिन. छोटे जैसा काम है. ठीक है, चेंजेस एवरीथिंग. सो आवर नेक्स्ट टॉपिक इज एक्चुअली इंशाल्लाह फ्रॉम नेक्स्ट वीक, दैट्स आवर नेक्स्ट मॉड्यूल, एनालिटिकल ज्योमेट्री. ओके, इस स्लाइड में ये दिया हुआ है, आप इसको देख लेना. गो थ्रू दीज. आई थिंक फर्स्ट टू यू ऑलरेडी डिड लास्ट वीक. अगर नहीं किया तो प्लीज़ कर लें. I've already uploaded these slides on LinkedIn at least, so उसमें देख लेना. और third one is also useful, that is the basics documentation of SciPy, right? So that's it. I want to finish linear algebra today, so let me close this and I can take questions and then we can go to your presentations.